Thank you. Good morning, everybody. As you said, my name is Syfy. I'm founder and managing director of Physician GmbH. We are a German company, and our main topic is finance, and for that we use Python a lot. We've developed a commercial derivatives analytics suite, which is available on the web. If you visit our website, and this is the first thing I want to do with you, to go to our website, www.physician.com. I hope it is readable. If not, here's physician again, .com. There you find the link. I show it on the website. Just give me a second. On the first page you find something like EuroPython 2012. If you follow this link, you will find another one which leads you to all the material that I will present today. You will find a link. I will do it for you, with you. If you follow the EuroPython 2012 link, you find a number of words, what we are doing here, and you find, by the way, the slides I presented yesterday in the talk Fast Data Mining with Pandas and PyTables, and you also find a link leading you to the training slides. If you download them, it is a zip file and it's password protected. The password is simply EuroPython 2012. In one word, the E in capital and the P in capital letters. So if you have that, you have everything you need for today. If there's anybody having trouble with it, just raise your hand and I try to help. It's written over there. The password is EuroPython 2012, written in this way. No slash, nothing, just one word. Capital E, capital P. Well, first of all, before we start, it's a little bit difficult to design a training which has a technical or industry background like finance, because you don't know what people you will confront in the training. So first of all, I want to ask the question, who of you has a background in finance, working, for example, for a bank or in derivatives analytics or somewhere else? Oh, it's only... Finance is quite a large field. Yes, I know that. So this is even not specified. When I talk about finance, usually it is mathematical finance. It's more like oriented towards derivatives models and so forth, simulation and that kind of stuff. But I have also brought something which is more from a broader context. But the other of you have more developer background, or what is your background? Maybe you can draw some hints. Okay, so this is quite, well, this is fine. Wonderful background. So adding a little bit of finance theory, it looks mainly the same. So I hope, but the focus will be on Python, of course, and how to implement stuff. It is really a large agenda that I've brought with. You see there are 96 slides in it. I've tried to structure it the following way. I will start with some useful Python libraries for finance. Then I will lay, from my point of view, the foundation with the use of Numpy. Then I will present how to implement... It's quite loud, isn't it? From the other room. It's actually louder than me. Yeah. Because I don't have any other three. Sorry? Can I go next door and ask them to... I think someone has already gone out. In this part I will just briefly illustrate some numerical topics which you might face when you work with such stuff. I will have some bigger case studies which I've considered too large to do like in a training, but when presented I've provided the whole script, so you can take a look at these scripts by yourself. You can check them, you can work with them. By the way, there is no guarantee, no representation for the scripts, but there's also no license attached to it, so you can freely use them. There's nothing special about it. Then we will go on to something we have seen in my talk yesterday, time series analysis with pandas. I've always included some kind of brief exercises, and then I want also add a case study which is a little bit longer and maybe too long to just do it together in the training. Then we have something about pi tables, how to use pi tables beneficially. I was a little bit surprised yesterday when I asked how many people know pi tables, that there are only, like, I don't know, 5 or 6 people raising their hands in my talk. In comparison to pandas, there have been more people, so this was a little bit surprising for me. But nevertheless, we will take a look at it, and I will present some stuff with regard to how to maybe implement some financial projects. If you have maybe a research background, doing research at the university or even at corporations, this could be beneficial for you. Just to close it up, I will just present some example code how to use Python to speed up, but we have experts in this regard here, like Mike, for example. This is not a topic of priority for me, but I think it's a large kind of stuff, and if we cannot go into detail with regard to the one or the other topic, then you will find everything in the slides and in the scripts. So don't worry if we don't get through it all. Once again, we have a number of issues that we want to address, but we cannot be exhaustive with regard to the Python capabilities in this field. As we said before, it's a large field, finance, so we can only touch upon some certain things that are important. What we want to do actually is to provide a first impression of Python's advantages for Python. For example, in comparison to C++, which is still dominating in the financial industry. And we want to lead you to further self-study, that you say, well, this is interesting for me, I didn't quite get it in the whole, but I can dig deeper and figure out how to use it for myself. As I said, the majority of the content is included in the slides. However, I have left out something, so there are 3 exercises where you won't find the solutions in the slides, but we can get through them together. The same slide as yesterday. I'm not a developer, so what we do today is not intended to teach you how to produce financial code which is ready for production. It's more like how to prototype, how to implement financial algorithms in Python. So things like exception handling and so forth, you won't find them in the scripts. It's just like the translation, and many times the one-to-one translation of financial algorithms and aspects into Python code. So be aware of it when you use it in practice, but as I said before, there's no warranty and no representation included in the scripts. To start with, and I have included this list also in the description of the training, what do we consider as important or beneficial libraries for finance? First of all, like the mother of everything that we do in scientific areas with Python is Numpy, which you need for array operations, and I sometimes say that finance is nothing else than array operations. You need them a lot, you need them all the time, and you have to manipulate them in a fast manner. Then Syfy, a scientific library which provides, among other, statistical functions. Matplotlib, if you want to generate 2D or 3D figures. Pandas, a time series and panel data library which facilitates a number of data analysis stuffs considerably. Pi tables, if you need a database which is optimized for fast calculations. So yesterday I said sometimes you have the case where maybe your data set doesn't fit in the memory, but you can nevertheless use Pi tables to implement fast calculations on your hard disk, and it won't take as long as, for example, with an SQL database. Python, if something is too slow from your perspective, you might take a look at Python, add some static typing, and maybe you can speed it up by a factor of 100, or sometimes in some cases, as examples show, you can speed Python code up like 1,000 times compared to pure Python. But if you do array operations right with Numpy, there's, at least from our perspective, hardly a need for the things we will see today. IPython, not actually library, is a little bit more, it's like a development environment, and I really enjoy using it in terms of interactivity. I don't know if you use it, but I like to use the Qt console, which have some nice features. So for people who are used to MATLAB, for example, they like such interactive chess. And Notebook, yes, Notebook is a new thing. I don't use it yet. Yeah, just to present, and I know some people change to Notebook to present stuff, which is also something from the mathematical world. but I'm still working with the Qt console shell. For your convenience, I've included in the slides links. You can just follow the links if you're missing something, maybe like pandas, for example. What I also want to suggest that you download maybe the Syfy lecture notes. They are quite good. I know they use them at EuroPython every year, and they're getting better. So it's a nice general introduction to Python from a scientific perspective. There you will find a lot of valuable basic information if you are not used to using Numpy, for example, just to touch upon one topic. For people who are more from an industry background and interested in Python packages and so forth, you might have a look at this link. There you find topical ordered listed software. So if you have a special topic in mind, you might find the solution in this quite exhaustive list. Why do we consider Python good for finance applications? As I said today, Python is used in the financial services industry, but for the core applications they typically use C++ and other compiled languages. I see a major benefit in the multi-purpose aspect of Python. For example, if you compare it to MATLAB or R, they are very good in what they do, but there are many other fields where these packages, specialized languages, are not that good. With Python, in principle at least, you can do everything you would like to do in terms of generating prototypes or even implementing production-ready applications. The productivity, I think, is much higher compared to other languages. You can seamlessly migrate from the prototype state to the development state. It is easy to maintain due to its compactness and readability. I often speak to people from investment banks. They have to maintain like financial models consisting of 50,000 lines of C++ code. People change over the years, so they have like half a year just to understand what other people have implemented and so forth. And if you consider this is only one model and they have like hundreds of models, you can imagine how many lines of code, C++ code, they have to maintain over the years. And I think Python has major advantages in this area. That is, you have compact code, and even if people haven't been involved in the development, they are quite fast in understanding what is going on in there. Low cost, of course, I don't have to say anything about that. It's future-proof, I think. It's becoming better and better, and huge development efforts around the world will make it even better in the future. And good performance. Yesterday we saw in a talk by Mike that it can be or is in many situations faster than Fortran. I like to compare it to C++ and other languages, or if you compare it to MATLAB, for example, you have at least the same performance. So I think performance isn't an issue anymore if you do it right, but we will get to that a little bit later on. Same slide as yesterday. Our experience with Python is manifold. We develop a commercial suite. We're doing research with Python. We give trainings like this, but mainly in a corporate environment usually. We use it in client projects. I use it as a lecturer at Saarland University, where I teach mathematical finance to illustrate the models, and I just recently finished a book which is called Derivatives Analytics with Python. Like 300 plus pages where I illustrate every financial model and everything that I do with the help of Python scripts. So we use it, as you see, in a number of areas. So I want to start with Numpy. As I said, the mother of everything else we will face today. Without Numpy, all the other stuff that we will see later on wouldn't work. So first my question, who uses Numpy? I don't want to ask who knows Numpy. Only a few of you use Numpy. I thought it would be the majority. Mike is still using it. Well, Numpy, as I write here, is a powerful library that allows array manipulations in a general sense, linear algebra, because there are a lot more functions in a compact format at high speed. The speed comes actually from the implementation in C. So to say is like a warp hole. If you give something to Numpy in the hands of Numpy, you are sure that it will be run on optimized C code and it won't run on the level of Python. So you have the convenience of Python on the one hand, very compact code, but combined with the speed of C. So if you use it right, you can have C performance, but nevertheless the elegance of Python code. How does it work in principle? These are just some examples which you might want to implement by yourself. You can follow them. You can, if you have your notebook up and running, if you import Numpy, everything from Numpy, you have something like a range, and if you say A is a range, which means you start at 0 in this case, go to 20, these are floats, compared to the range function that you have, which are based on integers, and your step size is 1, that you get something which looks like this. And you see here, this is an array, and the major advantage is that you can do a lot of stuff with arrays that would be like messy in pure Python. So for example, just to start with, you can resize this, or more reformat it. Resizing is a little bit confusing, but the size remains the same in terms of number of elements, but you reshape it more or less, that you say I want to have it 4 times 5. Then you have an array in this form. You see arrays are like vectors in mathematical terms, and you have it like matrices, 2-dimensional objects, but you can have it n-dimensionally. So it's very easy to have like n times m times j, for example, arrays. You can slice, dice, everything that you know of other stuff with the arrays. We say here, for example, give me the very first element of the array A. In this case, it will be the first row, as you see. You type in A types. So here you get the 4th row of it, the typical Python numbering starting at 0. But you can also say, give me a specific element, where you have like a vector notation, where you say, give me the second element from the last row in this case, and this is actually the D9. Oh, in the second row, the last element. Or you can have like slices, which says, for example, in the second line, give me from, you see, the third one to the second but last one, the 2 things. There are a number of conventions regarding array indices. If you take a look at the documentation, which is quite big right now, it is a topic for itself to learn Numpy, to use it rightly. If you take a look at it, you will find a number of things that you have to take into account when using these array structures. But my experience is, even experience with students, you have to play with these. You have just to get some example where you want to work on, and then you learn it best, because there are so many things you have to notice about it that it may be a little bit messy to read the whole documentation. So what you can do, and this is where the convenience comes in terms of financial calculations, is that you use these arrays as, for example, integers or floats. When you say you want to halve an integer, this is a typical operation. In Python, if A would be like an integer or a float, let's say, this would exactly look like this. And with Numpy, you get the convenience, for example, of MATLAB. MATLAB is the closest thing to Numpy that you can find, where you can have all these mathematical operations with regard to the arrays. You have like a matrix, we saw it before, and you just say A times 0.5. Then you halve the whole matrix in one single operation, and it's not done on the Python level, it is done on the C level, and it's executed quite fast. You can have like squares, you can add things together if the shape fits, of course. This is not as convenient as in pandas, where it's taken care of missing data. And Numpy requires you that if you add something up, that the shape is the same of the 2 things. This is like the broadcasting you have, of course. If it fits. This is true. Broadcasting upwards, but if you have like two-dimensional arrays and it doesn't fit, then it doesn't know how to broadcast it. But you're right, upwards it works, but not in this sense. What you will often encounter in finance, and I will talk about this in more detail later, is that you have algorithms which at first sight seem like you have to implement it by iterations, by loops, because you have more often than not in finance something like start with this and then go to the next step, then iterate over this and again, and everyone who is developing is like thinking of for loops or something else. You can do that even with the arrays, of course, because you can, using indices for example, and you can loop over this over this array. In this case it's again a one-dimensional array which has 50 elements. Or 51 elements, taking this, no, it's even more. We have a step size of 0.5. So you can loop over the array by just using the index. For example, looking for something that is of interest for you. You have functions like enumerate, where you get back the index itself and the value of it. But as we will see, just for completeness, I won't use it. Later on, if you do it right, all the algorithms that I will present will mainly I have to say, avoid loops on the Python level. It doesn't mean if you don't see a loop on the Python level that there's no looping on the C level in Numpy, because of course you have to iterate over the single elements of the array. But on the Python level we will see you can almost always avoid iterations if you do it right. What is also quite convenient from a finance perspective is that you can easily generate random numbers. Random numbers, especially when you think of simulation tasks, are necessary almost always, so you need them a lot. We use or we need them for almost everything we do. Our derivatives analytics suite is completely Monte Carlo based, so for everything we do we need random numbers, and to get them easily and in the shape or in the same format as we use for the other calculations is quite convenient. So if you import everything from numpy.random, you have a lot of functions available where you can generate like a single dimensional random number vectors, or you have in this case two-dimensional, but more often than not you will have multi-dimensional requirements, so you can generate them in the same way, 2 times 3 times 4, and you see here you have a multi-dimensional array with random numbers in the with the distribution that you required, and there are a number of distributions available. If not, you will find some additional ones in the Syfy library, but this the sub-library of Numpy is still quite good for our financial purposes. When working with arrays, and especially in a financial topic, you often want to visualize stuff that you have calculated, that you have simulated. You want maybe plot some stock prices as a path over time, which is a time series, or you maybe want to generate some histogram, and it is quite easy using a matplotlib pyplot to generate these two-dimensional plots. I haven't brought an example for the 3D plots, but in general it's enough to have 2D plots. So you see two main things. For example, you have here, you imported everything from matplotlib pyplot. You can plot B, which is an array. You just say plot this array. There are some options, for example crit, then you will get the crit on the figure, axis tied, this moves the axis to the data that you have provided, and then you type show, and a result might look like this, if this makes sense. I don't want to argue about it. These are just random numbers. This is a random number vector which we have generated before, and we have plotted them in a lines format. You have also a number of options in terms of if you want to have dots or lines, figure lines, colored lines, if you want to have bars, and every one of you who knows matplotlib knows that this is quite mighty. If you don't know it, just go to the website matplotlib. They have a very nice gallery where you just click on an icon in the gallery and you will get the complete source code. You can copy it, for example, to IPython, and you can put your data that you generated in it. So it's quite easy to apply this. can also generate subplots, because sometimes you want to compare data, or you have two different views on the same data, or you have two series or two different types of data that you want to combine in a single figure, for example, for reporting purposes. And what we want to do right now is to plot this random vector in two different ways. The first is that we plot it as dots. You see, as before I just said plot B, and in this case it generated by default lines. If I parameterize it in this way, then we will get red dots. You have to check the help file of plot to get all the options that you will have for the plot function. And we want to add as a subplot a bar plot. Here we have to provide a range for 20 numbers, and we also provide again the random number vector D, and the result might look like this. So again, it doesn't make sense from a technical point of view. These are just random numbers, which we plotted in this case as red dots. You see there is no grid because I haven't used the option to generate a grid. Here is a grid, and you see the same stuff as a bar plot. You can also change the middle point of the bars and everything else. As I said, matplotlib is quite mighty right now, so you will find a lot of options to visualize and to customize your figures. So this just was in a couple of minutes like a run through Numpy, only touching upon some important aspects, at least the ones that I consider important for financial purposes. Well, what I want to do with you right now is a little exercise. We have seen almost everything, or actually everything that we need to do what is written or asked here. And this, we want to generate two series with 50 standard normal pseudo-random numbers. They are not really random numbers, as we know. They are pseudo-random numbers. It is an array of size 102. I wrote 50, no, it must be 50 and 2. And we call it Rn. But it doesn't matter if you generate 2 times 100 numbers, so there's no problem with that. It's just not consistent what I wrote here. We want to calculate the sum of the two 50 number vectors once vector-wise, using Numpy as it is intended. There is a function which is called sum, simply. And we want to store it in another array. And we want to implement the second kind of thing where we want to loop I think we start with it. We just start with it. First thing, step by step. I don't want to explain it. If you have got through the first 2 steps, then we go one step further. So you have to import Numpy right now. If you haven't done it yet, you have to import. It is. Yeah, there are 2 different styles, and if you write something bigger, or you develop a huge solution with a number of modules with many things in it, and even if you work with the team where you have to distribute development, then you would do it the way as Mike described it, of course. You don't do it. But if you are scripting, it makes it a little bit faster if you don't have it. So. But you can do it both ways. You can import, you can star import it, or you can import it as NP. 564.
You override some and things like this.
Everyone else having difficulties downloading? If you just click on this.
That's too easy.
Ah, it was too easy. To click the link was too easy.
It's built in some which is different. This one is a sum of everything. Plus, say,
Depends on the access that you use.
two numbers.
No, the sum of two vectors. Is it, if you have a plus a as a vector, yeah. Just to make it clear, when you got it right, you have like two vectors with 50 elements stored in a single Numpy array, like 50 elements, and what I'm looking for is like the sum of the two vectors, so you have a vector operation. Yeah, this is true. This is what I just was doing here right now to show, depending on the shell or the tool you are using, you get some nice hints. For example, in IPython, as Mike said, you have the question mark help function, but it also supports you on the fly. For example, here in this case, if you say Rn is standard normal and you have the first parentheses opened, then it already gives you some hints with regard to parameterization of this particular function. Here in this case, it only expects the size. If you don't provide anything, then it will return a single random number. But you can have like 100 random numbers, or you can provide a different shape that you want to see. So size is not only one-dimensional in terms of the number of standard normal pseudo-random numbers that you want to get back. You can provide the shape, a multi-dimensional shape. And this is now printed out, what I try to illustrate over there. If you've typed it like this, you have like 250 element vectors. And what I said in the first is we want, after generating these two series, we want to calculate the sum of these vectors as a vector operation, and we want to store it in another vector, so to say, another array, Rn sum. And once again, if you use the sum function, imported Numpy, yeah, I can. This is quite easy. With my slides I can do it. In IPython I can. So you see here you need a little bit more. Or actually you don't need more, but you have more options to parameterize it. You provide the array where you want to calculate the sum over. But if you have a multi-dimensional array like this, of course there are a number of options with regard to the whole sum, or just the sum in the first dimension, or the sum over this. So you have to provide the axis where you want to calculate the sum over. Details at this stage we don't need this, but if we just put in our array that we generated, we get back the sum overall. So it's a sum over all the numbers that are stored in it. If it makes sense or not, this is another question, but it gives you, even for a multi-dimensional array, it gives you the overall sum. So if you want to just to add up via vector operation the two vectors, then you can specify the axis. And we do it once again we have the Rn array, and then we say we start with the 0, just see what happens. Okay, this is not what we meant to do, because again, with the vector operation, we will get a vector which has the same dimension as the first two vectors. So if we get out just a vector with 2 elements, obviously it is the wrong axis that we've chosen. It is. It depends on certain kinds of conventions. There is one difference indeed is that, but don't ask me which is the right one to do. You have some performance topics in terms of, usually you have matrices that look like this, but more like 100 times 50,000 or something. So if you have the bigger loop as the first loop, it is better from a performance perspective. It makes up for like 10-20% from the layout. Yeah, yeah.
So if you say array.flags, then you see the layout, and you can change the layout. See layout, and you can decide if you like to change the layout. And have big performance impact. Then performance impact, you load everything in cache. But next, and if you do it the wrong way, then that's
Yeah, but you can check by yourself if you have some special problem, and you can easily change the layout. So in this case we get back the array which consists of 50 elements. Next thing we want to do, just to illustrate some differences in terms of how to use Numpy in certain instances and maybe what to avoid. I want to start with calculating a cumulative sum, index by index, which means we take the first element, we add the second and store it somewhere, we add the third and store it somewhere, we add the fourth, and at the end we will have the cumulative sum over the whole vector. You need it for some purposes, but I just want to use this. We could have another example here, but I think it illustrates quite well how to work with Numpy arrays. We have in Rn sum now stored our sum over the two vectors. What we want to do is to generate another 50 element vector, that we get it right, not a single sum. We want to generate another vector, as I said, which adds up element by element the vector which we generated in the last step. So you can do it in two different ways. The first is, and I propose that we start with it, that we calculate it by cumSum, which is a Numpy function which you can apply to an array. And the second is just to implement a short loop where you do it by yourself. Because we saw it yesterday in a talk by Mike, and there was a discussion around this. People who are used to implement loops, they always try to translate what they learned maybe in Fortran and C and C++ to translate this to Python as well. So there is some kind of risk that you say, oh, I understand this algorithm, this is some kind of loop, and I want to implement it right now in Python, and you start looping over it and forgetting about to take a look at how you could do it better in Python. So we maybe start with the cumSum function, which is quite easy to apply. And then I would propose that you try to implement the same kind of thing as a loop over the array that we generated beforehand. So here you see our vector, and what we want to do is, in the first element of our rncum vector should stay this thing. This is the initialization. In the second place you will find the sum of both. In the third you will find the sum of the 3. In the fourth, the sum of the 4, and in the fifth, the sum of the first 5 elements, and so forth. As I said, you can do it like rncum /np sum, and you see once again you have to provide an array, and if you have a multi-dimensional array, you can once again specify the axis that you want to use, but in this case we have only a one-dimensional. And you see once again with Numpy we have had something which cries for a loop. But we have done it with a single function on the Numpy level. But nevertheless, I suggest that you just try to implement a simple loop where you implement this cumSum function by yourself, either by defining a function or by just implementing a loop. There are actually, I think, a number of ways how to attack this, but either one should be fine. Actually, what I've just done is to plot our rncum vector, which already looks like some kind of stock price development, or apart from being negative in some way, it's more like a profit and loss development. At least if you believe in efficient markets, yes. But random in what way? Random, of course, not in a normal distributed way. So this is. But for a long time, this was the major hypothesis, that everything is standard normally distributed. But as we know right now, we have fat tails, at least on the one end, so, and also skewness, which I describe in detail in this book, by the way. This doesn't look like a stock price development. It's more like an erratic thing, our random numbers. But if I use cumSum, it becomes more like a typical movement. Do you have your loops up and running? And in the end, you can easily compare it. If you have a second vector, you can subtract your result from the one that comes ungenerated, and you will see if it works correctly or not.
That was a question the guy had yesterday. How do you deal with subplots? I think it always work to answer for your client in let's say 2 ways. So you can check your own results. Do you do it that way?
Yeah, actually yes. But actually, it's a very good question, because with our software we have some kind of problems in this regard, because you can model derivatives where there are no benchmark models available. You know, typically when you say you implement a software, you have some standard cases like a test suite. You have the standard benchmark models, and you have your own results, and you benchmark them against well-known results from other approaches, from other formulas and so forth. But you don't have them every time, so you practically have no benchmark. This is a loophole. This is like having Excel. Microsoft won't guarantee that everything that is calculated with Excel is right in the sense that it makes economically sense. They say, well, 2 plus 2 is 4, hopefully, but if 4 makes sense in this context, nobody knows. And Microsoft would never guarantee it. And this is really a problem that we face, that if you allow people to model something, then they expect that it's correctly valued in the end. So we can't take any guarantee or representations for this. So. Yeah. Yeah, but this is same as with Excel. If they would say we buy a service from you, we give you some kind of model specification and so forth, and we expect fair values back, then it would be different. You know, then we would have the responsibility that it is correctly modeled, that there are no flaws, that it's valuable at all with our software and so forth. But if we just provide a software, you cannot. If you want to predict the lottery numbers for next Saturday with Excel and you fail in doing so, you cannot get to the court and try to sue Microsoft. So in front you see one possible implementation. I think there are a number of others. How to iterate over this? I just initialize a second vector which is the same size as our rnsum vector. I initialize the whole vector with my first value of the sum vector, and then I iterate step by step, adding step by step the next value. So and you see, in fact, this is some kind of looping operation. And this looping in Python, if you have large vectors, is time intensive. It needs a lot of time, especially when the operations are a little bit more complicated than summing up. You have my logarithms, exponents, and so forth. Then it will need a lot of time. But if you do these kind of operations on the Numpy level, then you will save time in a considerable way, not only in like 10% or 20%. You will speed it up more like 25, 30, 40%. It depends on 40 times. not percent, 40 times. Depends on what you are doing with it. With our algorithms, our financial algorithms, the speed up factor is like 25 to 30 times on average. Could be, yes. Because you have the overhead. Yeah. You have this overhead of the communication between the two words, so to say. And I just made a check over there, you see, where I subtracted the former result from my own result, and you see it's fortunately always 0, which means that the results are the same. So maybe next step, to come to an end with this exercise, you might want to plot the R&COM vector that you have now calculated. You can plot your own, or you can plot the result of the COM-SUM operation. And as a second exercise in terms of plotting, you should try to plot the two 50 random number vectors as histograms and to put it into a single figure as subplots. Again, we saw everything before. If you take a look at the slides and the examples that I provided before, you should be able to do that quite easily. Sorry? Does it work? No? Oh, it's a big one. It's a big one, but it's a good one. So. Standard Normal und dann muss man nochmal einen Vektor auch übergeben. Also, genau. Das ist die Subbibliothek Numpy.random. Also ist das dann COM-SUM-Vektor? Ja, deswegen, der wird anders aussehen, das ist mir klar. Aber ist egal. Ist jetzt nur. Wie gesagt, das ist so der erste Schritt Richtung Finanzserie. Wenn man es logarithmiert, könnten das ja Renditen sein. Also es könnten logarithmierte Renditen sein, die sich aufaddieren und subtrahieren. Das ist dann deine Entwicklung. Also im Prinzip eigentlich relativ gut nachvollziehbar hier an der Stelle. Oh, sorry. I was talking to two guys in German, and I was now in German mode. What we want to do is to generate two different figures. The one is just the COMSUM vector that we want to plot. It looks like, as I said before, like a stock price development, and the second is a figure with two subplots, where we just provide the position for the subplots, and then first the histogram for our first vector, and second the histogram for our second vector. Yeah.
You can just say, if an IPython say percent, and then you have some interactive thing. You just say, yes, you take a percent, and then it says you have a plot, and then the percent sign, percent pilot.
And if you do from or import
Yeah, and then say from matplot import pyplot.
pyplot, yeah.
I think it might block as soon as you show the figure of blocks. If you build in pilot, it doesn't. So you can change your figure and see it updated live. If you start IPython, say IPython minus pilot, and then it's importing everything, import Numpy and
Syfy.
for interactive programming, it's easier.
So the two figures could look like this. Of course, you will most probably see different figures because we are working with pseudo-random numbers, so your numbers won't be the same as mine. Here we see the first one, our COMSUM plotted. Looks like a fair game in the long run. It doesn't have to be. And the second figure we generated are the two histograms as subplots in a single figure. You can have also four subplots in a single figure or whatever. For example, if we're working with pandas, what we will do shortly, you have convenient functions where you, for example, can plot a data frame when it has like 4 different time series. It will automatically generate 4 different subplots for each time series stored in the data frame. But here, as you saw, it's quite easy to do it on the fly as well.
It has a notion of the writer's code. You want to make a reference, then you need to change the reference. Sometimes you want to make a reference, then you can have many figures, you can work with many figures. But here, if you work with actively, it gives you the last one you used to with the original one. If you don't have a reference in the one before, it's gone. Create a reference. Just say left-hand side as 1 equals subplot as 2 equals, and then most of the time if you call something, you use the object you can work with.
Just means on the command as a method.
Most of the things are there as a function and a method.
Yeah.
They are both the same. So you just it's a long list of things.
Numbering of the subplots? 2 to 1.
It's a little bit confusing.
It's
Yeah.
because you have 2 by 2, you have 2 rows and columns, and then it's number 1, 2, 3, 4, 5. So you have like a 2-fold, and you have 2 rows. I think it's rows first and then columns. Rows, and then how many columns you have in total, and then the last number gives you.
This is like 2 rows and with only 1 column. You see? 2 rows, 1 column, and this is first, second. Otherwise, you would have, if you have two columns, of course, it's like 2, 2, 2, 2, 1, 2. So it's like matrix style, or is it MATLAB oriented? Add it to it, yeah. You can change later what's upwards, or you can, for example, I could add some label to it, or switch on the grid, or whatever, in the subplot.
When I show, there is no figure count,
So, but it did. But it did say that it generated something beforehand. Yeah, that is behind your window, your current window, or somewhere. Okay, sorry.
So I do figure,
Yeah.
and it correctly says that I have the objects, and I do show this.
Yeah, but this is empty. You haven't plotted something to it.
It should, okay.
Yeah, sometimes it shows the empty plot, but
I did the plot also, but so figure, then plot this. Oh, it's the other interpreter. Sorry. Here.
okay. You have to import it from.
Yeah, it's like this here.
Yeah.
And then I left show.
But you have
I've used the Matplotlib, but it's the first time. Maybe it's the EuroPython sometime.
it can be that you don't have installed the right graphical backend. You need something like Qt, or depends on, I don't know the dependencies of the Matplotlib library, so it could be that you need some kind of graphical backend which is not installed. So for what I'm doing, I need the Qt backend. Yeah. But typically it's at least on Ubuntu, what you use is it's installed on the fly, so I don't know. Yeah.
I installed now Matplotlib with this PIP.
Maybe you should give it a try by the Synaptics package manager, I don't know. Because it takes care of all the dependencies. If you go... Oh, it worked? But if you go to Synaptics, you don't have the package. But is Ubuntu? Is Ubuntu, yeah. Or package, if you type package.
Oh, there is this software.
Yeah, software. Actually not.
We installed it.
Maybe there's something different in your installation, so sorry. Okay. I think for everyone working in finance or close to finance or working in some similar field of expertise, Numpy is a very mighty library you might always give a try if you are working with data structures. So it is quite fundamental. We have right now, I have to take a look at my clock, how much time is left. We have about 25 minutes. So the next topics are only some kind of brief topics where you might get an impression how to work with some convenient functions which are mostly out of the Syfy library. For example, what we have to use quite often, but in almost any field of finance you have to approximate stuff. Approximate in a sense that you have a number of observations wherever they come from the stock market or from a physical experiment or biological kind of thing, and you want to infer something, you want to describe what you see, you want, well, in a general sense, to approximate something. So you have different ways to do that. The first and most simple one maybe is regression. Regression for us, at least, is one of the most important things that we do, because the majority of our algorithms is mostly based on a core step which includes regression. So we use it a lot and we need it a lot. And with Python, in combination with Numpy, it's quite easy to implement regressions. So what I want to illustrate is the most simple case, ordinary least squares regression, where some kind of optimization function is minimized in that case, and where we work with ordinary monomials, x squared, x cubed, and we want to approximate a desired function given a number big N, capital N of observations, which might look like this. And once again, this could be financial numbers, these could be physical numbers, biological stuff, or wherever you work, and you want to approximate it maybe by a polynomial of order 2, but as we will see, we can easily scale it to include higher polynomials. What you can also easily do is to have a multivariate kind of thing where you have different different variables which drive your function, which means that x becomes a vector and is not a float or something else. The task in this case is to minimize the sum over these, but there's something missing I see right now. There should be a square in it because it's least squares, so there is a typo on this in this formula. We want to minimize the sum over absolute numbers and not something where we might get negative as well as positive numbers, but hopefully in Python it's correctly implemented. Just a simple example, which is quite artificial, but it illustrates what we can do with it. We may have some numbers, like 20 observations for the cosine function over the interval from 0 to half p. And we want to approximate this function via polyfit and polyval. These are two functions which you find in the Numpy library as well. From polyfit you get the minimizing regression parameters back. These were the A's of the last slide. Well, you can use these, then plug them in, so to say, in the polyval function to generate values based on these parameters. What you see here is just a really simple example. We generate these 20 observations for the cosine function, and I want to illustrate like an approximation, a regression with a constant number, which a linear function, and with a quadratic function. But you can easily scale it to include like the cube and even higher monomials into this. When we get back our regression parameters, we put them into the polyval function, use our 20 observation points, and want then graphically compare how good our estimates, our regression functions approximate the cosine function. You will find this script if you want to load it, if you want to check it by yourself, in the folder which you have downloaded, which is called topics. There you find something called a rec. And if you execute it, you might see something like that. You see the yellow line here. This is the cosine function. We have the minimizing constant number, which means it was the first regression we did just by a constant figure. We then have the linear regression, which are the blue dots, and we have the quadratic function from the quadratic approximation. You see it below there, the green triangles, which is already quite good. It's not perfect, but for this purpose it would suffice. As simple, yes.
Like, it's only short parts because I have one longer part would be like piecewise.
Yeah.
Great, we can use this function for this.
It's my next.
Oh, sorry.
Is my next thing. Oh, no problem. But it's not actually piecewise regression because this would be a little bit messy because you would have to take care of all the interval limits. You know, if you have like 3, 4, then how to get it smooth, how to get it continuous. These are problem. So, but it's a good issue raised by Mike because quite often, at least in what we do, we face stuff which is not strictly convex or concave. So in this case it's quite simple because we have like a monotonically decreasing function which is quite smooth. So we are able to approximate it quite well. But for example, I've worked on a payoff which looks quite simple. In a sense it is simple. But it's quite hard to approximate by regression. So you can imagine if you have something, I've had another, there it is. If you have such a non-convex payoff, of course you can have something like your constant number, you have something like linear would maybe be the same, but if you start having something like a cube, not a cube, but a quadratic function, and you have something like this doesn't approximate well this area. You know, then you start with a cube thing. This would maybe look like this. It approximates this quite well, but this really worse. So if you work only in this part of your payoff, wonderful. But if you have this payoff, you have to take care of the whole range of possible values. So there is no way out of this trap, but as Mike already suggested, to take some kind of different approach to it. So one approach which works quite good in a low dimension is to use splines, which is the concept of interpolation. It is mathematically much more involved, but in applications it is almost the same, almost as straightforward as using regression. So you have in the submodule of Syfy interpolate, you will find the functions that you need for the use of cubic splines. Here in this case, we want to use the same numbers. And what do cubic splines do in effect? Cubic splines is like a form of intelligent regression. Once again, if you have something like this, like a non-convex payoff, and cubic splines just say you have a number of intervals that you consider separately, and for each interval you have your regression function. And as the name suggests, the regression function is one that is a cubic function, so you have at least enough freedom for the interval. And what it does in addition, this is the kind of thing that we are often interested in, it smoothes it out on every interval limit. So maybe you are not perfect here, but one thing is to make sure that you have a continuous, even twice differentiable function in the end. This is what you often need when you do financial applications, and you will be able, via cubic splines, to approximate such a function quite well, because you have lots of intervals. You can scale it, of course, you can say how large the interval should be, and it makes life much more easier, especially in cases where you need the approximate function that you get from your cubic splines expertise and have to differentiate it. This is often the case if you work with rate curves. If you have something to do with interest rates, interest rate related products, then you have some set of yield observations where you say for this duration the yield is like 1%, 5 years plus is like 10%, and so forth, and you have a number of discrete observations, but you need something that approximates this, that is differentiable afterwards. And you have to make sure that it's differentiable no matter what happens over there. And there you want to use, for example, cubic splines to interpolate your observations. It is something that is better in terms of results for certain conditions, but you have to to take care of the ordering. For regression-based approximation, it doesn't matter if you have an ordered set of observation in the direction of your variables, for example. The axis, so to say, can come in any order. But if you want to use cubic splines, of course, you must take care of the single observations that lie in the single intervals. The approximation by regressions is more like a global thing, so it doesn't matter in which order you put in your observations, because if it's globally done, it doesn't matter if it's in the first place or it's in the last one, it gets the same weight. But if you want to work with intervals, of course you have to respect the structure that you want to impose. So if you have some set which is not ordered, you would have to order your numbers first and then apply cubic splines to what you observe. And what is another limitation, in some certain sense, is that cubic splines are of limited or even no use for higher dimensional problems. There are some approaches where you can have multivariate observations and it still works. But in general, for higher dimensional problems, you don't have anything else but regression to make the approximations. But at least, as we will see in this short example, when we use cubic splines to approximate our cosine function over the given interval, 0 to half p, and it is done via these two functions, splines, rep and splines evaluate, and you see the output. Of course you find this in the same folder, this brief script in the same folder as I mentioned before, and you see the result is in this case perfect. You know, you will touch upon every observation point. You will touch it perfectly, and not only like differences of minor order or something. You see this already looks like the stuff. Yeah. Yes. Yeah. This is what we do. Of course, if we do this kind of payoff with regression, then we also use this perfect function, you know, as the approximation, because we know a little bit about the structure, and in this case, it's like obvious because we are working two-dimensional and so forth. But we will face cases where you don't have any clue which function to include to improve your approximation. Of course, the example with polyfit, it's just the basic example when you use polyfit and polyval is like the standard regression method built in a Numpy. You can use the least square solver where you can include any function that you can imagine. This is what we actually do with our application as well. Excuse me? I still didn't get it. If you set up your problem by yourself, not in polyfit. In polyfit it's just like monomials that you can use. You can only scale in terms of order. But if you use least squares, then you define your functions by yourself. You build your approximation problem by yourself. Then it minimizes the problem that you provided. So you have full flexibility. Either monomials or whatever, or combinations, cross products, you can include everything. Another drawback, just to mention it as a last point in this regard, is that it's quite time-consuming. Cubic spline computations need time. Regression is done really fast, but cubic splines are a little bit fast, but if the result is much, much better, you may consider it nevertheless. Then another typical object or topic in finance is optimization. Strictly speaking, what we saw before are already two cases of optimization, but in a more general sense you will face some functions that you either want to maximize, like utility or whatever you face in finance or economics, or that you want to minimize. One of our standard problems is to minimize an error function. When we calibrate models, the model has maybe like 5, 7 or 12 input parameters, and we want to calibrate the model to observe market prices that we see in the option markets, and to to this end, we already know beforehand that there will be no perfect fit. We are not able to calibrate the model perfectly, but what we can do is to minimize the error function. So we say, okay, our results that the model generates are benchmarked against the results we observe in the market, and maybe we want to do something like we have seen before. We want to minimize the squared differences between it. So this is like a typical problem that you see, where you have in general two major approaches. The one is a global one, where, as I said before, if you have 5 input parameters for a model and you want to minimize your function globally, then you would like to apply maybe some kind of brute force algorithm, where you say start with the first parameter at 0 and iterate in 0.1 steps to until you reach 2 and so forth, so that you like flying all over the whole world and take a look at least briefly at every spot that you see in the world, and then maybe as a next step, or you even start with a local optimization, say, well, this seems promising and we now want to dig a little bit deeper and we want to locally take a look at it and to optimize it a little bit better. Then you have a number of functions available that you can use with Python, or I must say Syfy as well. Here quite a really simple example once again, where we have again a trigonometric function given, like the scene function. Very simple example. We take the sine function over the interval from minus p to 0 with a minimum value of -1 at half p. Again, we know it, but we are interested how Python works it out, and the library Syfy has these functions stored in the submodule optimize. And you see here once again you will find it in the same folder once again, and what we do here is we just want to apply the brute force algorithm, which is called brute in Syfy, to the problem, where we say just start iterating at -p, stop at 0, this is the interval that we're interested in, and go by the step size. Finish none just means that there is no rule in terms of when to finish this. He has to do it no matter what the results are in between. And then you have the function for local minimization, fmin. This is only one option out of a number of, I guess, 10 different local minimizers that you will find in the library. Here I just say minimize y, this function, and start at -1/2 or whatever. You don't have to give a starting point, but in a certain sense it speeds it up, of course, if you have some knowledge about the structure and you have some guess where it would be good to find it. So here in this case, it's really a simple example, but what we use it, there are very highly structured functions that we have to minimize, but the same approach still works very well in a multi-dimensional world. So what I try here is just to give a very simple example, but you can apply it to as complex functions as you usually face in your daily work. So the first, as we see here, is a global minimum. It was spit out as -1.57. This is about half p, and the local minimum, which the local minimizer generated, is almost the same. And we see here it needed 18 iterations, and it called the function 36 times. So you have some kind of additional information. If you like to, you can get even some more information about the local minimization process. As you know, in this case I haven't read it out. I just printed the result here, but as I said before, you get some more information from the local minimization algorithm generally than just the number that turned out at this stage. One of the last small topics which you might face in finance is numerical integration. More often than not, you face a function which you can't integrate analytically. What you will find in Syfy, once again, libraries to do integration stuff, numerical integration stuff. And here again an example where we know the analytical value of the integral exactly. In this case just the exponential function over the interval from 0 to 1, and the value is approximately 1.7 something. Syfy helps out in this case. In this case, we use numerical quadrature scheme to do this, and once again, it seems quite easy to do this, and you can do this with much more complicated functions, as in this case. But this is a very simple one. We have just the exponential functions, and we want to get the value of the integral. I'm just interested in the first item of the vector, which is given back by the function. Over this function from the interval which starts at 0 and goes to 1. For us, we need it quite often when we have to numerically evaluate integrals with regard to option valuation functions. These integrals are quite complex, involving characteristic functions and so forth. There we have some imaginary stuff and so forth, but still Syfy integrate helps you out with this. As I mentioned before, just a simple example to give you hints where to look for, but you can apply it to much more complicated stuff that you will face in practice. So I think this is the right point to get to the coffee break, and afterwards we will go on with some financial stuff, which is a little bit more involved. But first a question, typically the coffee break is like 45 minutes. Do we need the 45 minutes, or should we do it a little bit shorter and have a little bit more time for the stuff that follows afterwards? Should we do 20 minutes break? Is it okay? Okay. Should enough for the coffee and some sweets, and then see you again later. At 10:50, yeah. We see each other again at 10:50 here in the room.